In this video, we're going to be talking about prime factorization of numbers, starting with a couple definitions. So we need to start by defining what the natural numbers are. The natural numbers are positive whole numbers, so like 1, 2, 3, 4, 5, etc. No zero on that list, and indeed no negatives, no decimals, no fractions. So those are the natural numbers. Factors are going to be natural numbers that go into something evenly. So if I'm looking for the factors of 24, I'm looking for only the positive whole numbers that can go into 24 evenly. So if I'm listing out the factors of 24, I can start from the number 1, which I know goes into 24 evenly, and just keep rising and check in my mind if 24 can be divided by the next number. So can it be divided by 2? Yes, without a remainder. It can be divided by 3. It can be divided by 4. Can't be divided by 5 without getting a decimal result. It can be divided by 6, not by 7. It can be divided by 8, and so on, to create the whole list of numbers that 24 can be divided by. So those are the factors of 24. The numbers that go into 24 evenly that are not decimals, not negative, not fractions. And it can be helpful to think about these in pairs, right? 1 times 24 creates 24. 2 times 12, 3 times 8, 4 times 6. Factors are always going to travel in pairs to create a number. That pair method might be helpful if you have to list the factors of a larger number, like 84. If I'm listing out the factors, I like to list them in order from least to greatest, but it can be hard to do that. So when I'm thinking about 84, I know it's divisible by 1. I'm going to move way down the list and put the number 84 because that's the pair, right? 1 times 84. Does 2 go into 84? It does. If I need to check on a calculator because I can't divide it in my head, I'm going to do 84 divided by 2 and see what the pair is that goes with it, and it's 42, right? Put that down the list over here. Check if 84 is divisible by 3 if you're not sure, and indeed it is divisible by 3. When you do 84 divided by 3, it'll tell you that the pair that goes with 3 is 28. So I can put that further down my list. Check if it's divisible by 4. It definitely is. When I divide 84 by 4, I'm going to get 21. Check if it's divisible by 5. I know it's not because it doesn't end in a 5 or a 0. If it's divisible by 6, which it is, right? 84 divided by 6 gives us 14. My gosh, I'm running out of space. There's so many things that 84 is divisible by. You can check if it's divisible by 7, and you might be surprised to find out that it is divisible by 7, and that's paired with 12. And then I can check 8 and 9 and 10 and 11, which are the ones in the middle there between 7 and 12, and see that it's not going to be divisible by 8, 9, 10, or 11, and therefore that's my complete list of the factors of 84. So it might help you to do it in that pair method. Just make sure you leave enough space for yourself to fill in all the pairs in the middle. Further definition, so prime numbers. A prime number is a natural number, which we've already defined, greater than 1, that has only itself and 1 as factors. So important that it's greater than 1. And it's important that, of course, a prime number has only itself and 1 as factors. So if I'm thinking about a prime number, I'm thinking like 2 is a prime number, 3 is a prime number, 5 is a prime number. And notice I skipped over 4 because 4 has itself, also 1, and also 2. Thinking a prime number 7. 9 is not a prime number because you can divide it by 3. Notice I'm not putting any other even numbers on this list because all even numbers can be divided by 2. 11 would be on this list, 13. 15 doesn't go on the list because it's divisible by 3 and 5. 17, and so on. So these are the prime numbers. Numbers that can only be divided by 1 and themselves. And the list starts with 2 because the definition of prime number says that it has to be greater than 1. So 1 itself is not prime. You may want to write that for yourself. That's what it says at the bottom. The number 1 is neither prime nor composite. Composite numbers are all the other ones. The natural numbers greater than 1 that are divisible by multiple things. So like 4 and 6 and 9. The Fundamental Theorem of Arithmetic, which is every bit as important as it sounds, says that every composite number can be expressed as a product of prime numbers in one and only one way. What this means is, like, if you take any composite number, and the example here is 700, but I'm going to start with a smaller one. The example of 20, right? There's a way to write the number 20 as the product, which means multiplication, of prime numbers. So if I think about the number 20, I could write it as 4 times 5, right? But 4 is not a prime number. 5 is, but 4 is not. But I can further break down that 4. I can write 4 as 2 times 2, And 2 is prime, and 5 is prime. So I could think about the number 20 as being written 2 times 2 times 5. That would be called the prime factorization of 20. So the fundamental theorem of arithmetic says every single number, every composite number, can be written as the product of primes. And if you do it and I do it and he does it and she does it, we're all going to end up with the same product of primes. That's what it means by in one and only one way, if you ignore the order, right? Somebody else may come up with 5 times 2 times 2, but that does mean the same thing. So there's only one way to write the number 20 as a product of prime numbers. So everybody will factor it down the same way. The best way to do it is to create a factor tree, which you might have done before. So now we'll create a factor tree for the number 700, which is the one this example has here. So to start with a 700, you write it at the top, and then you can split 700 using this little tree illustration into any two factors that create the number 700. Generally, if it's an even number, you could just divide it by 2 and use a calculator if you need to, because 2 is an easy one to see. If it's even, 2 is going to go into it. So 700 breaks into 2 times 350. I can use a calculator to check that if I need to. 2 is done. 2 is a prime number, and I can't break it down any further. But 350 is not prime. I can certainly break that down further. And like my advice was, if it looks even, which it does because it ends in a 0, try dividing it on the calculator and break it into 2 times whatever pair it goes with, so 175. Now, 175 is not even, so it's not going to be divisible by 2. But I can tell it's divisible by 5, so I'll break it into 5 times whatever pair goes with 5. Go to my calculator, divide 175 by 5, and it's 35. Another one that I can see is divisible by 5. Whoops. That was supposed to be the number 5. And the pair that goes with 5 is 7. And now I've got to the end of every branch ending at a prime number, right? I can't break any of the ends of these branches down any further because they're all prime at the end. So I'm going to circle the numbers that are prime so you can see the ends of the branches that I'm talking about here. So this is a prime 2. This is a prime 2, this is a prime 5, a prime 5, and a prime 7, right? There's no way to break any of those down any further other than times 1, right? So once you figured out all your primes at the ends of these branches, the prime factorization is going to be 2 times 2 times 5 times 5 times 7. Right, working backwards, if I multiply these all together, the 7 times 5 gives me the 35, times another 5 gives me the 175, times a 2 gives me 350, times another 2 gives me 700. So this result does equal 700. It's a different way of writing 700 as the product of prime factors. You'll probably see these written in exponential form, right? 2 squared, because there's 2 of them, times 5 squared, because there's 2 of those, times 7. So this is the prime factorization of the number 700. All right, and then the last 2 slides are just more practice here. Note that if the numbers are small, you may be asked to do it without a calculator, so you should practice doing it. If the numbers are large, you might be asked to do it with a calculator. I'll just do one more, so you might want to pause and try it on your own, and then check back and see how your answer looks. So I'm going to prime factorize 120, figure out the prime factorization of 120. I can see it's even, so I'll split it into 2 times 60. 60 is even, 2 times 30. 30 is even, it's 2 times 15. 15 is not even, but I can see it's divisible by 5, which is prime, and I know 5 times 3. And now I'm down to only prime numbers. So I'm looking at a 2, a 2, a 2, a 5, and a 3. Notice I'm only circling the primes. And so 2 to the 3rd power times 5 times 3. The order in which you write those doesn't really matter in the end. Most books you'll see would write them in size order. So 2 to the 3rd times 3 times 5. And then there's a couple more examples for you to practice the prime factorizations of. And that's all.